Good morning, boys and girls, and welcome back. Today, we're going to start with a little review of the four Maclaurin series that we should have memorized, or Taylor series that we should have memorized. And then we're going to use that. I'm going to show you a quick, neat little trick you can use with those. Again, another reason why we want to have those four memorized. And then we're going to get into the real talk about Taylor's theorem, which is also known as Lagrange error bound. Okay? I'm getting to talk again about our error with this stuff. But first, let's go review those four Maclaurin series that we should know. And here they are. E to the x, again, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Skipping to the bottom, because I kind of put these two together in my mind. 1 over 1 minus x is 1 plus x squared plus x cubed without the factorials. Okay, so I kind of keep those similar. Sine x is my odd function, so it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And cosine is even, so it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And both sine and cosine alternate. Okay. Again, you just want to have these down and get those memorized. And again, here is why. If I want to write the Taylor series for x e to the x, I really don't want to have to go find the derivatives. If I had to do this, if I wanted to go find, let's say, the third degree Taylor, polynomial approximation, for this, I really don't want to go find like the three derivatives. If I do that, I'm going to have to use like the product rule a bunch of times. Okay. I believe this is one off the homework actually you guys did last night. You probably had to go do a bunch of different, derivatives unless you were smart about this. A better way to do this is, if I know e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, then I can just multiply this Taylor polynomial. Again, these things are interchangeable. Like we talked about yesterday, you can substitute in, or you can take the derivative or integrate them. I can manipulate these just like I would the expression itself. So I can just take x and multiply it by all this. And so my third degree approximation, polynomial approximation, would be x plus x squared plus x cubed over 2 factorial. I don't even need to go grab that third one then at the very end. Okay? So this would, you can see, makes your life a little bit nicer. That's a lot easier than having to find all those derivatives using the product property and everything. Same idea on this one. You got to know which one you're playing around with, but this looks kind of like our 1 over 1 minus x. I just got to maybe move things around a little bit to get it to work. I can rewrite 1 over x plus 1 as 1 over 1 plus x, which is 1 over 1 minus a negative x. And so now I can use this rule, but instead of plugging in x, I'm going to plug in a negative x instead. Again, if I know that the Maclaurin series for 1 over 1 minus x is that, what I can do then with this one is I can, instead of plugging in x, which we plug in here, I can substitute in negative x. So this polynomial would be 1 plus negative x squared plus negative x cubed. Or if I simplify that, I basically get a little alternating series going on here. All right. So all these, again, just different ways to, different easier ways, cooler ways, kind of a neat trick that we have to, more easily write a lot of our Taylor polynomials. All right. Maybe I'll just do one or two more so you can see it from last night's homework. Okay, so next, getting a little trickier here. We're going to do 1 over x. I want a fourth degree polynomial approximation. But now I'm going to want it centered at 1 instead of centered at 0, okay? So I'm going to have to shift my center here as well. So here's how I'm going to do this. You probably can guess that we are going to need to use this Maclaurin series, okay? The one for 1 over 1 minus x again. But I'm going to have to do some modifying to get it to work just right. So I'm going to have the 1 over x written in the 1 over 1 minus something form. I'm going to have to change things. But I want to make sure that when I'm all said and done, it still equals 1 over x. It's just written in a different form. So I need 1 over 1 minus, and now I need it centered at 1. So if it's centered at 1, then we have an x minus c thing going on, right? An x minus 1 right there. That'll center it now. However, if I try to simplify this is going to be 1 over 2 minus x, which is not what I need. So I need to, again, adapt this a little bit more. And maybe if we put a little negative 1 in front like this. Now if I were to simplify, just to make sure again that they're the same thing, I would get 1 over 1 minus negative x plus 1, or 1 over 1 plus x minus 1, or 1 over x. So this is the same thing as 1 over x. Again, it's just written in a different form, okay? And now, because it's in this form, all the stuff that's in the green here, the green parentheses, if I plug that into the Taylor series for 1 over 1 minus x, this will now give me the Taylor series for 1 over x. So the Taylor series for 1 over 1 minus x again is 1 plus x squared plus x cubed plus x to the fourth. And so now I'm just going to have to plug all this stuff in right here in for my x's. And we do something like that right there when I plug the negative 1 times x minus 1 in. And now if I simplify this, I'm going to end up with 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed. And so there's my, there's my Taylor polynomial that is centered at 1 for 1 over x. Pretty cool. All right, one last one real fast. All right, if we want the Maclaurin series with an n of 4, and again, centered at 1 for ln of x. All right? Well, ln of x, again, we don't have one that's like ln of x. However, again, keeping in mind a relationship between things, I do know that ln of x is the antiderivative of 1 over x, right? And on the problem we just got done doing, I know that 1 over x is, well, not 1 over x necessarily, but 1 over x centered at 1, which is what I want anyway from the problem before, is 1 minus x minus 1 plus x minus 2 squared minus x minus 1 cubed. And so what we can do is I could take our series that we got before, and I could go and integrate this using u sub, and then I would have my answer. I'm not going to go through that. I just want to kind of talk about the steps on how to come up with this. Forget it. Maybe I will just real fast. And so this would be our 4th degree polynomial centered at 1 for ln of x, okay? But again, the point behind this is we can manipulate these series that we know to come up with new and different series, and we generally can do it a lot easier than if I were trying to, like, again, take the derivative 4 times of this thing. That would not be very fun, okay? Okay, now it's time to talk about Taylor's theorem or Lagrange error bound. All right, so this all is going to stem from the idea that, again, these Taylor polynomials, Maclaurin polynomials, are used to approximate a function. That if we were to go to infinity, an infinite number of terms, that our Taylor polynomial approximation would equal the function, be the same thing. Now again, our issue is we can't go to an infinite number of terms, so there's always going to be some error or some offness in our approximation. And back when we talked about alternating series, we called this amount of error our remainder, right? So the real value of the function plus the approximation, or the real value of the function is going to equal the approximation plus some remainder, some amount of error from the original thing, okay? So this is all we're kind of building off that idea right there. And this is for, again, some Taylor polynomial written generally as f of c plus f prime of c times x minus c over 1 factorial, f double prime of c times x minus c squared over 2 factorial, and so on to some nth degree, right? All right, so what Taylor's theorem or Lagrange error balance says is that there's going to be some value z that is between the x that we're trying to find and the c that it is centered, okay, some point between those two things, that the remainder is going to equal, again, what this is basically saying, kind of like an alternating series, is that next neglected term. The derivative of f of n plus 1, that next term that I don't go to, so that some value z times x minus c to the n plus 1 over n plus 1 factorial. And I kind of relate this back to that next forgotten term, that first neglected term. Okay? So there's going to be some z value that's going to make the remainder equal to, if I used it, equal to the amount of error. Now this is kind of an issue though. We know there's some z value that should be there. We just don't know how to find that z value. So what we tend to do is we tend to rewrite this and change this just a little bit so that I can use it. And if I just reorder things a little bit here, and I move the x minus c on top of the n plus 1 factorial, and I move this f of n plus 1, the derivative, to the back here, okay, so this is the same thing, I just kind of change things around. What we can say, though, is that even though I can't find this derivative at z, I can say, well, what is the max derivative that it could be? If I know the max, then I know my error is always going to have to be less than or equal to that amount. Okay, so that's what Lagrange error bound is saying, or Taylor's theorem is saying, is that we can find some value. I don't know that that is going to be my error, but I know my error would have to be less than that amount then. Okay, so here's how we can kind of use that idea. We're going to use the third degree polynomial to approximate sine of 0.1, and then we're going to determine the accuracy of our approximation within a certain range. All right? So first I need to find my third degree polynomial. So we know that sine is approximately equal to the third degree Taylor polynomial, so x minus x cubed over 3 factorial. And I'm going to want to evaluate this at 0.1. And if I plug in 0.1, and if I were to evaluate that on my calculator, I'd get 0.099833333. Now the question just becomes, how accurate is that? Well, let's go and look at the remainder then, that part that's left over, and see if we can't find that. So again, to find the remainder, you want to be thinking about the next neglected term, right? So I'm going to look at the fourth degree, the derivative at some value z, which again, I don't know, 0.1 to the fourth, because that's my x over 4 factorial. But again, I don't know this part right here. And that's kind of where we get stuck. And because we can't find that piece right there, what we're really going to look at is this modified version. Again, where I have all the same pieces, we just kind of change the order around a little bit. My x to the fourth over 4 factorial, that's the next forgotten term, times that max derivative, right? So we're going to do 0.1 to the fourth over 4 factorial. Now the max derivative, in this case, I don't have to actually go find the derivative, the fourth derivative of sine. It's either going to be sine or cosine. And I just know that the max derivative, the biggest that sine or cosine can be then is 1. So that would be my max derivative, okay? And now I can go evaluate this, and I get the remainder using this third degree approximation is going to be less than or equal to 0.0000416. So we're pretty accurate, okay? I know that the real value, if I add this to my approximation and subtract from my approximation, I know that the real value would have to be between, and so the real value would have to be between those two values right there. And if I added my error and subtracted my error from my approximation. So that's pretty cool. We know that we can be actually pretty accurate with these Taylor polynomials. Okay, so here's another example. I want to use Taylor's theorem or Lagrange error bound to obtain an upper bound for the error of this approximation. I know that e is 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial and so on. If I'm looking at this, I know that this is an approximation to the fifth power. So if I wanted to find my error or the remainder, I'd find the remainder with an n of 5. All right? And again, to do this, again, I always remember, it's the next neglected term, or the term. So the next neglected term in this case for e would be x to the 6 over 6 factorial times that derivative. And again, I don't know what that derivative is, so we just say that max derivative, right? Whatever the max could be. And so to find this here, I know that the remainder is going to be less than or equal to 1 to the 6 over 6 factorial. Since, again, e to the x, we're really evaluating that x is 1, right? Times that max derivative. Now, here's kind of the tricky part in this case. Well, what is the max derivative? Well, the first derivative of e to the x is e to the x. The second derivative of e to the x is e to the x, all the way down, so on and so forth. The sixth derivative of e to the x is e to the x. And again, we're evaluating this at 1 now. So I guess the max derivative would be e to the first. And so if we work this out on the calculator, that means my upper bound, or the maximum amount of error I'm going to have for my approximation then, is 0.003775. So again, that is a relatively small amount of error. That's pretty good. Okay, so last one here. Let's say that we are back in the old days. Well, I can say don't have a calculator, but we're going to use one here anyway in a second. But I want to, I want to find cosine of 0.1, but I want the error in my approximation to be less than 1,000. Less than 0.001. Okay. What degree of a Maclaurin polynomial do I need to use in order for my error to be that small? All right. So this is how we would set that up. First, just as a review, that would be the Maclaurin polynomial that we would use. And just in general, that's our formula for the remainder of a, Taylor polynomial. And so again, in this case, to find my error, my x is 0.1, I'm evaluating it at. The n plus 1 degree, again, I don't know what degree I'm going to, so that's what I'm leaving it as n over n plus 1 factorial. And again, for cosine, the max derivative is going to be 1. All right? So now what I need to do is I just need to plug this into my calculator, and I want to know when this amount right here is going to be less than or equal to 0.001. And so I said less than or equal to, I just mean less than 0.001. So I'm going to plug my remainder into y equals, and then I'm going to go to my table, and when I look at my table, Again, for my remainder to be less than 0.001, then I have to have two terms. So I'd only need a second degree polynomial. And that's it, boys and girls. Have a good day.